Imagine a place where gravity reigns supreme, a place so dense not even light can escape its grasp. This is the realm of black holes, enigmatic objects scattered throughout the universe. Among them are the supermassive black holes, colossal entities lurking at the heart of galaxies, including our own Milky Way. Think of a black hole like a cosmic vacuum cleaner, relentlessly pulling in anything that ventures too close. But unlike a vacuum cleaner, a black hole's pull is so strong that nothing, not even light, can escape its clutches once it crosses a certain boundary known as the event horizon. Supermassive black holes are the heavyweights of the black hole family. They can be millions or even billions of times more massive than our sun, crammed into a space smaller than our solar system. By understanding these cosmic behemoths, we gain insights into the fundamental laws of physics and the evolution of galaxies, including our own. Supermassive black holes are not just big versions of regular black holes, they are in a league of their own, distinguished by their extraordinary mass and their location at the centers of galaxies. Picture a region in space where an enormous amount of matter is squeezed into an incredibly small volume. The gravitational pull of this concentrated mass becomes so intense that it warps the fabric of space-time, creating an abyss from which nothing can escape. These objects are not holes in the traditional sense but rather regions of extreme density with gravitational pull so strong that it distorts our understanding of space and time. The event horizon of a supermassive black hole marks the point of no return. Anything crossing this boundary, whether it be a star, a planet, or even light itself, is inexorably drawn inward, fated to be consumed by the singularity at the black hole's core. The formation of supermassive black holes is one of the most intriguing mysteries in astrophysics. How do these colossal objects, millions to billions of times the mass of our sun, arise in the first place? While definitive answers remain elusive, several theories attempt to explain their origins. One leading theory suggests that supermassive black holes are born from the remnants of the first stars in the universe. When these stars exhausted their fuel, they collapsed under their own gravity, forming black holes that served as seeds for future growth. Another theory proposes that supermassive black holes form through the runaway merger of smaller black holes in densely populated regions of the early universe. A third possibility involves the direct collapse of massive gas clouds in the early universe. These clouds could have bypassed the star formation stage altogether and collapsed directly into black holes, providing a rapid pathway for the formation of supermassive black holes. By studying these objects, we can gain insights into the processes that shape the cosmos in its infancy. Supermassive black holes are not merely passive dwellers at the centers of galaxies, they are active architects, shaping the evolution of their host galaxies over billions of years. Their immense gravitational influence governs the motion of stars and gas, sculpting the galactic landscape and regulating star formation. One way supermassive black holes influence their galaxies is through the accretion of matter. As gas and dust spiral inward toward a black hole, they form a swirling disk of material known as an accretion disk. This disk heats up due to friction, emitting intense radiation across the electromagnetic spectrum, making the black hole visible despite its inherent darkness. The energy released by the accretion disk can drive powerful outflows of gas, known as jets, that extend thousands of light-years from the black hole. These jets heat the surrounding gas, suppressing star formation in their vicinity. This feedback mechanism plays a crucial role in regulating the growth of galaxies, preventing them from becoming too massive too quickly. When galaxies collide, their central black holes can spiral toward each other, eventually merging in a cataclysmic event that releases vast amounts of energy. By studying this interplay, we can gain a deeper understanding of the processes that govern the evolution of galaxies and the cosmic web of structures they inhabit. Section 5. A Dance of Gravity. Physics at Play. Supermassive black holes are not just astronomical objects, they are cosmic laboratories that allow us to test the limits of our understanding of physics, particularly Einstein's theory of general relativity. This theory, which describes gravity as the curvature of space-time caused by mass and energy, has been spectacularly successful in predicting the behavior of gravity in extreme environments like those found around black holes. One of the most intriguing predictions of general relativity is the existence of gravitational waves. ripples, in the fabric of space-time, caused by the acceleration of massive objects. The merger of two black holes, for instance, releases an enormous amount of energy in the form of gravitational waves, which propagate outward at the speed of light. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the groundbreaking detection of gravitational waves from the merger of two stellar mass black holes, confirming a key prediction of Einstein's theory. This discovery opened a new window into the universe, allowing us to study objects and events that are invisible to traditional telescopes. Supermassive black holes, with their immense masses and strong gravitational fields, are prime candidates for future gravitational wave observations. The detection of gravitational waves from the merger of two supermassive black holes would provide unprecedented insights into the dynamics of these extreme objects and the physics at play in the strongest gravitational fields in the universe. Section 6. Seeing the invisible, observing the unseeable. Black holes by their very nature are invisible to telescopes that collect light. However, their immense gravity and the energetic processes occurring around them provide telltale signatures that allow us to detect and study these enigmatic objects indirectly. One way to see a supermassive black hole is by observing its effects on nearby stars. As stars orbit a black hole, their paths are altered by the black hole's gravity, causing them to speed up and change direction. By carefully measuring the motions of stars in the vicinity of a suspected black hole, astronomers can infer its presence and estimate its mass. Another method involves observing the radiation emitted by the accretion disk surrounding a black hole. The Event Horizon Telescope, a global network of radio telescopes, made history in 2019 by capturing the first ever image of the shadow of a supermassive black hole located at the center of the galaxy M87. By combining observations across multiple wavelengths, astronomers can piece together a more complete picture of the structure and behavior of supermassive black holes and their surrounding environments. Section 7. Echoes from the Abyss, Unveiling Black Hole. Secrets. Supermassive black holes are not just cosmic enigmas, they are also time capsules, preserving information about the history of their host galaxies and the early universe. By studying the properties of these objects and their surroundings, astronomers can unravel secrets about the evolution of galaxies and the conditions that prevailed in the early cosmos. One way to probe the history of a supermassive black hole is to study its spin. As a black hole accretes matter over time, it can spin up, much like a spinning top. The rate at which a black hole spins can provide clues about its past accretion history and the properties of the material it has consumed. Another avenue of research involves studying the chemical composition of the gas and stars surrounding a supermassive black hole. By analyzing the light from quasars, extremely luminous objects powered by supermassive black holes in the early universe, astronomers can study the properties of gas clouds at a time when the universe was young and galaxies were forming. Section 8. The Future of the Unknown, Research and Discoveries. The study of supermassive black holes is still in its infancy, with many unanswered questions and exciting discoveries awaiting us on the horizon. As technology advances and new telescopes come online, we can expect to make significant strides in our understanding of these enigmatic objects and their role in the universe. One area of active research is the search for intermediate mass black holes, hypothetical objects with masses between those of stellar mass black holes and supermassive black holes. These elusive objects could bridge the gap between the two known populations of black holes and provide crucial insights into the formation and evolution of supermassive black holes. Another promising avenue is the development of more sensitive gravitational wave detectors. These instruments will be able to detect gravitational waves from the merger of supermassive black holes at greater distances, allowing us to probe the population of these objects in the early universe and study the dynamics of galaxy mergers in unprecedented detail. Section 9. Our Place in the Cosmos. Philosophical Implications. The study of supermassive black holes is not just a scientific endeavor, it is also a philosophical journey that forces us to confront our place in the vastness of the cosmos. These enigmatic objects, with their immense power and mysterious nature, challenge our understanding of the universe and raise profound questions about our own existence. The realization that supermassive black holes lurk at the hearts of most galaxies, including our own Milky Way, underscores the interconnectedness of cosmic phenomena. The processes that govern these celestial giants are intimately linked to the evolution of stars, galaxies, and the universe itself. The study of black holes also raises questions about the limits of human knowledge. These objects represent some of the most extreme environments in the universe, where our current understanding of physics breaks down. By confronting these mysteries, we push the boundaries of our scientific understanding and expand our appreciation for the complexity and wonder of the cosmos. Ultimately, the study of supermassive black holes reminds us of the vastness and mystery of the universe we inhabit.